So first of all, for me, it's a great pleasure to participate in this meeting, and I thank Alessandro and all organizers for setting up this nice conference. And let me say a few words before I will come to the topic of my talk. So I don't need to remind you that we're talking about fundamental changes in theoretical physics. And if you're thinking about those challenges which stayed with us for the last decades, there is one particular problem which I'd like to draw your attention. And actually, this problem appeared one of the millennium problems, which we put forward some time ago, which goes under the name of the proving confinement. And I believe this is a very fundamental problem, which will still in the center of development many years to go. And more or less, the question, the kind of provocative question which I would like to put forward is what did we learn about this problem over the last few decades of development of DCFT and studies in subconformal gauge theories? At the end of the day, we are here just to solve challenging problems of theoretical physics. So we have some experience over a few decades of development of strongly coupled theories. And basically, the goal of my talk to show that in some situation you could profit from the knowledge which you acquired over the last few decades to solve really practical questions which has to do with the phenomenology. So the goal of my talk to show that there is very concrete phenomenological problems which goes under the name of energy correlation, which you could get hint of using this machinery which you developed using superconformal gauge theories. And what I'm going to talk is based on some joint work done is together with Dima Checherian, Emily Sakachev, and Alexander Zhipoyedov, and I invite you to look for that paper for the further details. So let me introduce you in the field which we're going to discuss. So I told you we're going to talk about confinement. Confinement is synonymous that we have a problem in QCD. The problem goes as follows. When you formulate QCD Lagrangian, and it's formulated in terms of macroscopic degrees of freedom with quarks and gluons, and we know how to do theoretical calculation framework of those microscopic degrees of freedom. But when you come to the experiment, what you actually observe are not those degrees of freedom. What you observe is the bound states, hadrons. And this mismatch between microscopic and macroscopic degrees of freedom, which poses a lot of problems. Just to make it very concrete, let me show you this cartoon, which more or less indicates what goes on at LHC. So in LHC, you have two beams of protons which colliding, producing many very energetic particles, quarks and gluons. We start moving apart. How does it? Yeah, they start moving apart until they separate sufficiently fast so that corresponding energy becomes small. And at that moment, hadronization phenomena kicks in, which converts quarks and gluons into hadrons. And once you look for macroscopic distances from the collision point where your detectors, colorimeters are located, what you detect is not the quarks and gluons by hadrons. And fundamental question which people asked many years ago, given the fact that there is this phenomena of hadronization, how can you make any prediction if you don't control this transition, hadronization transition between two processes? So one possibility is self-confinement, and clearly we're not there yet, but there is another proposal which actually already existed for more than 4 decades, which is, goes under the name of quark-hadron duality. And the idea is quite simple. The idea is that is to define certain set of the quantities, observable quantities, which are called inclusive hadronic observables, such that computing those quantities short distances, which means in terms of quarks and gluons, you're expecting to get something which will match experimental observations up to corrections which will die out if you go to the limit infinite energies. So those observables, the inclusive hadronic observables, in general have this form. So you have some quantity which calculated at large energy scales, Q square, and you're expecting that computing this quantity in perturbation theory, dealing with quarks and gluons, expanding in powers of the effective coupling constant, which is alpha s of Q square, which famously has property of decreasing at large Q square, would allow you to get some reasonable prediction up to some corrections, which goes under the name of hadronization corrections. And as I repeat once again, those hadronization corrections for this class of the observable are expecting to vanish as inverse power of larger momenta. So now let's be more concrete. Let's go to LHC and see what actually happens at LHC. So you look for a particular event, and what you see here is actual event which has been taken by SMS collaboration. You could see there is some stamp indicating exact locations and point time, which shows you what actually observed at LHC. So what observed at LHC, here you have the special points, and these points, when two collision beams, which are orthogonal to the plane, collide, so there is some collision point, like Big Bang, a lot of energy is deposited at that point. You have production of many, many particles which start flying away, so you see all these green tracks, these are particles which move away, until they approach some microscopic distances. When all those colorimeters are located, the colorimeter detect different parameters of the particles. So they detect direction in which particles moves, and they detect the energy that particle deposed in those colorimeters. So what you see here, so those rectangle of different color, the shape, the area of the rectangle correspond basically the energy which was deposited on this colorimeter. So now if you look carefully at this picture, you will see that you have many, many particles produced, but those particles have a tendency to be kind of agonized in a very special way. So you have a bunch of very energetic particles which have kind of collimated beam. So those collimated beams of particles whose momenta aligned all in direction are called jets. And then what you see on this picture goes under the name of the multi-jet final states. So in general, any typical event in LHC, you have a lot of particles which form jets, and what you observe in the final state, something like this. So now, following the philosophy I presented you previously, you want to find some class of the observable which would be able to compute using available technique, which would allow you to characterize this particular event. And there is many different proposals, different observables, and the one which I will be concentrated on is based on very simple observation that energy is a very good quantum number. And you could see there's a lot of energetic particle deposit. So let's think about this picture as if you were talking about correlation of energy deposited in different locations on the circle, and you could think about the circle as like cut of the sphere. So imagine you have some sphere surrounding your collision points, detectors everywhere, the particles fly away, they deposit the energy, you know in which direction energy goes, and you're asking the question, what is the correlation between energy deposited in different points on this celestial sphere? So this observable is exactly what we're going to discuss, energy-energy correlation. So energy-energy correlation have been introduced in QCD back to 78. And once again, these are very simple observable, which has very simple physical meaning. Observable, which measures the correlation of energies deposited in different points of celestial sphere, so depicted here. So you're thinking about this picture, so here on the gray blob, Big Bang happened. So there was some collision which released a lot of energy, particles flying away. So you go on some microscopic distances, and you're asking the question, what's the correlation between energy which was deposited in particular direction over here, direction over there? So there's an angle between these two directions defined by some variable chi. So in practical terms, the quantity you're dealing with is this energy-energy correlation, which depends on the relative angle between detected particles, which obviously runs from 0 to pi. And if you want to compute this quantity, which goes under the name of EEC, or energy and correlation, you have to look for a quantity like that, when the first factor is differential cross-section, another way, probability to create particular final states with the particle distributed in a funny way, and you put inside this differential cross-section this special factor, which measures the energy deposited in the colorimeter under condition that the amount of particles which enter colorimeter is separated by the angle chi. And capital Q is the total energy, center of mass energy. So they're very simple observables. And once again, if you just follow this idea of quark hadron duality, what you will be doing, you will be computing this quantity in theoretical QCD in terms of the quarks and gluons, and you will be comparing this quantity to observation which are done in terms of the hadron. And if you believe the quark hadron duality, you're expecting to find that for sufficient large energies Q, this calculation you did in the theory should match observation done by experimentalists, provided the energy is sufficiently large. So this quantity have been measured quite intensively over more than 4 decades, starting from DAISY machine and then later at CERN lab machine. And here I'm just giving you a cartoon of the measurement which were done for not the final state which I presented previously, but the final states corresponding to your plus or minus annihilation. So you have your plus and minus electron positron which annihilate, producing a virtual photon, which in the final state decays into the hadron, and you're looking for the correlation of the energy deposited by the hadron on your celestial sphere. So we have very, very precise experimental data, and those data shown here on this plot. So let me explain you what's shown here. So on the vertical axis, this is this quantity which I introduced, your energy correlation. On horizontal axis, I plot cosinus of the separation angle, which always can run from -1 to 1. So this one corresponds to the angle being 0. This -1 corresponds to the angle being pi. And what you see here, black dots, they correspond to the observation data points taken by Delphi collaboration in the time. And what you see here, like red points, those come from the prediction made in QCD. And QCD prediction, it took some time actually to compute those predictions. So the first calculation, lowest order coupling constant, was done back to 78. Its coupling constant defined as some scale Q, times some function A, which you explicitly know. And then you could see it took 40 years to do the next order calculation. And the reason for this large time gap is not because people are stupid, because calculation is very complicated. Then if you're brave enough, you could ask the question, what will happen if you continue further? And you do have to continue further, because if you just see in this plot, you will see that the accuracy, theoretical accuracy actually is much better than theoretical uncertainty. So if it took 40 years to go from one loop to two loop, you could estimate how much time it will take to get the next loop. And what does it mean? It means that actually we have to develop much more efficient way to do the calculation. So this calculation, which were done both at one and two loop, were based on the standard techniques, based on static amplitude. And more or less, you see these techniques reaches its limit, and you have to do something else. And actually, one of the things which happened over the last few decades, that people indeed found the way how you could do the calculation, not in QCD yet, but in kind of cousin of QCD theory, which we all love, which is NFL4 macrosymmetric Young-Mills theory. I will explain you later what was the magic there, but let me just emphasize that right now in this particular theory we already have 3 loop results, so this correction is known. And we have a prediction at strong coupling as well. So let's now, excuse me, one thing which I forgot to mention, sorry, to go backward. Yeah, one thing which I forgot to mention, what's special about this picture? So you have this picture which has very characteristic shape. You see it's kind of function which is peaked around the endpoint. So why it's peaked around the endpoint? So let's look on the horizontal axis. So you have cosine of the angle, -1 and 1. So let's first think about this point. So -1 corresponds to the correlation angle being pi. And the fact that function is shaped around this point is synonymous. The corresponding final state has very special form. It has only 2 jets which go back to back, and clearly the most energy which will deposit in the final state will correspond if you put the detector back to back. And this is the reason why this function is peaked around these special points. But now you go to the opposite limit, this limit. So it corresponds to the chi going to 0, which means we're talking about correlation of the energy within particles belonging to the same jet. And it will be this region which we're going to investigate. And the reason why it's peaked here clearly is that you have very energetic jet. If you're looking for correlation of particles within the same jets, jet very energetic, you expect it to have some enhancement, and this explains why this peak appears as well. So in general, such kind of picture, even if you didn't know what was calculation behind, looking at the picture, you immediately conclude that you're dealing with 2-jet event. And now imagine if experimentalists did their measurement and they found something which were flat. So imagine instead of have this function like that, you will have just constant value. What does it mean? It would mean that it doesn't matter how you put colorimeters, the energy doesn't depend on the angular distribution, which means that energy is homogeneously distributed on the celestial sphere. So therefore, this shape of this function automatically gives you information about how the final states look like. So what I'm going to do, I want to concentrate on this particular region. So we're going to discuss the region when we're looking for the inside the jet, and we try to find the correlation between particles within the same jet. Why? Because in this way, energy correlation will give you some information about how actually the jet is organized. So how does the jet rise? So I already sketched the mechanisms. So you start with energetic particles, for example, quark, which was produced at short distances, and then it flies away, producing a lot of radiations, quarks, gluons, which at some moment get hadronized, and then they reach colorimeter, and you measure the correlation between hadrons located within the small jet, with the corresponding angle between N1 and N2, there's a vector defining the position of a colorimeter of celestial sphere, separated by angle chi, and we're going to look for the region when chi is small. So once again, you turn on this philosophy, you want to compute this quantity perturbation theory. So you compute the perturbative expansion in the path of the coupling constant, and then you're hoping the hybridization correction will be small. So then let's look what we expect from this perturbative piece. So perturbative piece will describe this branching process. So you have quark going into bunch of gluons quarks, and so that invariant mass, so the jet which produced, has characteristic energy which scales like center of mass energy multiplied by the angle chi. So if angle chi is small, invariant mass also gets smaller. And if you do the calculation, you will find the corresponding probability, the corresponding contribution to energy correlation scales as inverse angle. I remind you, angle is small, in some power which is 2, it's like kinematical power, minus some anomalous dimension which you compute order by order in QCD. But what's important that if you look for the argument of coupling constants, since it runs, it defines on the scale which is Q, large scale, times the angle. And once you have such kind of behavior, you immediately realize that something goes on. Namely, if you go to extremely small values of the angle, so that Q times angle becomes of order lambda QCD, coupling constant blows up. What does it mean? That means the perturbation theory indicates you that some new physics, non-perturbative physics, will appear for the angle of order lambda QCD divided by Q, which is small, but still it's there. So now let's ask the question, what actually happens based on experimental observation when you approach such small value of the angle? So obviously you expect the perturbation theory will not be applicable, so you're entirely in a perturbative regime. So how does this function will look like if you really go to that small region? And this question has been addressed recently by people which you see here on the slide. What these people did, they looked for the so-called SMS open data. So this is the data we could find on the internet, and then you could compute any observable you like using those data, and they use those data to compute energy correlations. They look particularly into this region. So let me explain you what you see on this plot. So once again, on horizontal axis, you have angle. So this is angle chi, which I introduced previously. Notice this is logarithmic scale. And the vertical axis, they put so-called normalized EEC. Normalized, it's, if you translate into my notation, it means that we have this EEC we've seen previously, you multiply by chi square. So this chi square slightly modifies the behavior, which we will discuss in a second. So what you see in this picture, and once again, these are experimental data. These are what experimentalists measure. So what you see that if you start from some relatively small values of the angle, you see 10 minus 1. So you have something which has very smooth flat behavior, and then you go to very, very small values of the angle, you hit exactly the value of the angle when you're expecting the perturbative physics kick in, and indeed there's some transition region after which the shape of the function changes. So once again, these are data, and this data know about non-perturbative physics. So now let's try to decode this non-perturbative physics into something which I told you previously. So first of all, let's take, please.
So you said that that's an experimental result. I mean, is there any way to be sure that this region of quarks and gluon is there? Can you directly or indirectly know that there are?
Forget about what's written there. Forget free hadron transition formula. This is interpretation. So these black crosses, this is experimental data.
Okay.
What's written above is the interpretation of those data.
Yes.
Okay? So let's distinguish two things, data and interpretation. What's shown here, this is data. Now you have to interpret this data using what you know. And as you could guess, what's written above, this interpretation, this region which is shown here in blue, could be interpreted in terms of the perturbative QCD, quarks and gluon. Then there is this transition region which corresponds to hadronization. This is exactly the region when quarks and gluons get transformed to the hadron. And then if you go to extremely small values of the angle, this becomes entirely an non-perturbative region when you're not even allowed to talk about quarks and gluons, you talk about hadrons. Okay? But now if you remove this chi square out of the definition, if you draw this figure slightly differently, just taking out chi square, what you will find that these two different regions, blue and green one, have different behavior as a function of the angle. So this part, which seems to be like a linear rising function, after you take out this chi square, actually becomes flat. So this behavior, this region here, from point of view of energy correlations themselves, correspond to the flat region. Flat region, I remind you, the distribution, celestial sphere full of the energy, there is no jets. And now if you go to the region which is here shown in blue, which seems kind of flat, after this chi square removal, it becomes actually a region when energy correlations growing. So you clearly see that non-predictability physics leads to these two different regimes, and there is some transition between two regimes which happens exactly for the values of the angle which I spotted you previously. Now the question, could we explain this transition and the underlying mechanisms which are responsible for the change of the behavior if you go from predictability to predictive cascade? And my point, which I'm trying to convince you later, that physics behind this transition has to do with the fact that you're dealing here with a big number of particles produced. Another way, we knew from the very beginning that LHC, you have a lot of particles produced, a lot of multiplicity of particles. And now the idea is that let's take this fact for granted and let's try to use multiplicity of particles as the new expansion parameter. Another way, what I want to do, I want to expand my energy correlation in inverse powers of multiplicity. To do so, I have to come up with some model. So let's start from the simple model. And the simplest model you can consider free scalar theory, no interaction. So how could I get large multiplicity? So I start with some operator, which is phi in power k, and I excite vacuum with this operator. What will happen if I excite vacuum with this operator? I obviously produce k scalar particles, which go in the final state with no interaction. So you could ask the question, what would be the contribution to the energy correlation in this situation? So you look for correlations of energy correlation between, let's say, m different detectors, n1, etc., and m direction of the celestial sphere. You look for the differential cross-section producing big number of particles in final states, and you compute this integral of including differential cross-section, including some additional factor indicating the particles go in direction defined by the colorimeter. So it's already at this level, computing this integral is not simple. But if you go to the limit when this k, I remind you, k is the number of particles in final state becomes large, you will see some remarkable simplification. So you have final states which has total energy, capital Q, and you're producing a lot of particles. Sum of energies of those particles should be equal to Q. But number of particles is infinitely large. So what does it mean? It means each individual particle will have infinitesimal momentum, infinitesimal energy. So if you rescale energy appropriately, you will find that in terms of those variable epsilon, which I put here, the corresponding integral of phase space of many particles actually simplifies enormously, and you get at the end something which looks like ensemble of particles whose energy is distributed according to this exponential law. But most remarkably, if you're thinking about how does dependence as angle enters, you could explicitly check the dependence as angle suppressed by the multiplicity. So what does it mean? It means that if you go to the limit where multiplicity goes to infinity, you will get in the free series the result, which looks like this. So some kinematical factor, 1, no dependence on the angle, and dependence on the angle becomes suppressed by 1 over k. So you have, roughly speaking, situation which we've seen in strong coupling. The dependence on the angle appears suppressed by small parameter. And indeed, what happens that some time ago, Hoffman and Maldacena, they looked for energy correlations in strongly interacting angle for theory, and they found that in the limit, when coupling constant goes to infinity, using calculation of strong coupling from a DSFT, they found that energy correlations have exactly the same behavior. Namely, in the limit lambda goes to infinity, energy correlation approach constant, and all dependence of the angle suppressed by 1 of the lambda. So in both cases, you have more or less the same behavior. So there is no jets, energy is homogeneously distributed in the celestial sphere. My mechanism is different. In the first case, in the case of free scalar theory, it was due to the fact that we produced a lot of particles and we went to the limit when number of those particles is infinite. Whereas in the second limit, you start from finite number of particles, you turn on interaction, and because interaction is infinitely large, it immediately populated your phase space with infinite number of particles. So these are different mechanisms which at the end gave rise to the same final states. Please.
Well, the formula is so different. One is 1 over lambda, the other is 1 over k.
Yes, because once again, this formula 1 over k, it was obtained in the limit. It was lambda equal to 0, but k large. So you have function which depends on two parameters, coupling constant and k. Now I'm asking the question, what will happen if I go for this function at two different limits? One limit, I fix lambda and I send k to infinity. And another limit, I fix k and I send lambda to infinity. These are two different limits. I'm saying in both limits, you get the same result. To linear order, indeed. But next step, we will address the question what will happen at the level of those suppressed correction. But the stance right now, in the limit when k goes to infinity, lambda finite, and lambda to infinity k is fixed, you have the same result. And I said mechanisms is completely different. So now let's turn on direction, right? So now we want to deal with our theory, doesn't matter, QCD, scalar theory, whatever, and now you have to find the way how you could compute these energy correlations in interacting theory for arbitrary value coupling constant. Obviously, this is a very complicated issue. And the way how you could address the question, you have to go away from perturbation theory. You don't want to have something which is intrinsically perturbative. And to do so, you have to rely on yet another formulation of energy-energy correlations, which was developed a long time ago, which is based on very special operators, which are called energy flow or energy flux operator, which defined here. So you have stress energy momentum. You look for the projection of stress energy momentum in a particular direction, and you do some stretch manipulation. So you're integrating over time, and you send special coordinates infinity along certain directions and put in front some factor r square. So what's remarkable about this operator, if you take matrix element of this operator with respect to some particular final states, you will see that the matrix element will pick up exactly particles which go in the direction defined by vector n, and they give you a result which exactly the one which measures the energy flux in this direction. So once you have this operator at your disposal, you could show that energy-energy correlation for any value of the coupling constant, which is given by Fourier integral like that. When you have two operators OK, those which producing your final states with large multiplicity of particles. In previous case, it was 5 pi OK. And now you have insertion of two additional operators which are there to mimic colorimeters. So these two operators effectively measure the flux of the energy in the direction of N1 and 2. So now once you have a definition of operators, etc., you combine them together, this becomes kind of very complicated formula you have to deal with. But what I want to emphasize is that if you just take away the integral, what stands inside, you have 4-point correlation function. And let me find this is a Whiteman correlation function. This is not the one which you get used to, the Whiteman correlation function. Operators are not ordered, which involves 4 operators. Two of these operators are heavy because you have final states with large multiplicity, and you have two stress energy tensor. So at that moment, you see that the next step to compute energy-energy correlation, you have to provide information about 4-point correlation function involving two stress energy tensor in two infinitely heavy operators. And this quantity is exactly the one which you start analyzing using IDS-CFT setup. So what could we say about this function? So at this moment, okay, we don't have much information except for n equal 4 theory. Let's concentrate on n equal 4 theory when you have this powerful technique which I described previously. And then you have a lot of things like comes as a bonus. The first thing, because you have maximal supersymmetry, you could show that this correlation function which you need, the one which involves, the one which involves two heavy scalar operators and two energy tensor, but the Bukhafor-Watt identity is related to a much simpler function which involves only half BPS operators with different weight. Two of them are light, two are infinitely heavy. And this correlation function has been studied quite extensively in the literature, and we know by now this correlation function in n equal 4 theory up to 3 loop at V coupling, and we know also at strong coupling, including corrections coming from supergravity and the strings. Hopefully, in some nearest future, we'll know it's for any values coupling constants and integrability, but for the moment, let's concentrate what we know. So now what you do, you combine information that you have, so you plug in into this formal expression for 4-point correlation function n equal 4 theory, and you go to the strong coupling, this limit which I mentioned previously. So you go to the limit when lambda goes to infinity much faster than k. K is multiplicity of particles produced. And then you recover Hofmann-Maldacino result, which is the one you see here. So I remind you it was a constant plus terms which one over lambda suppressed, and here you have very explicit expression which involves dependence on the angle. So z is related to the angle variable. And as I already emphasized, if you go to the limit lambda to infinity, this term goes away and you have constant distribution depending on the angle. But now let's go to the opposite limit. So let's go to the limit when lambda is fixed, and let's send k to infinity. Then you could show that for any value of the coupling constant, which is finite, which means much smaller than k, this energy-energy correlation has a form which is constant plus 1 of k times multiplies the function, which itself depends both on the coupling constant and angular variable. So this function is kind of new ingredient. But what's important, this function comes with 1 over k, so therefore you have more or less the same feature as before. But now let's look for this function f. So this function f could be computed at V coupling because we have quite a number of information. And let's see how this function looks like if you go to the limit when variable z goes to 0. So now we're zooming into the region when we're talking about correlation between particles within the same jet, the small angle limit. So you have your perturbative expansion. So these are Born level contributions, which we already knew was a constant. Then you have 1 loop corrections, 2 loop corrections, and 3 loop corrections. So now if you go to the limit, z goes to 0, even though functions quite complicated defined by 3z, for small z they simplify. For example, this function becomes 1 over k, 1 over z. So this 1 over k factor is in common. You have 1 over z coming from here. You go to 2 loop, you find 1 over z log z, some enhancement by log. And then you could show that if you continue further, this log will exponentiate. So the final expression will look like that. So you have constant term plus something depending on the coupling constant, 1 over k, and z in some power, which also depend on a. So this result was obtained using the coupling expansion, and then you ask the question, what will happen if you go to arbitrary value of the coupling constant? At that moment, you have yet another powerful method, which based on so-called OP expansion on celestial sphere, which was developed in parallel. And if you follow this OP analysis, you will find that what you expect in general, based on general ground, that this function f, of which energetic relation, should have a form like that. So you have identity operator contributing, which gives you 1, and then you have contribution of some so-called special light rate operator with certain quantum numbers, and their contribution scale with the coefficient function, which has this form, z in power 1 minus anomalous dimension divided by 2. Now, if you match what you have in perturbation theory and what you have here, there is perfect match. Namely, you could deduce out of these two formulas anomalous dimension at V coupling, and also you could deduce the matrix element which stands here in the numerator. Actually, it scales like 1 over k. This information is sufficient to explain the physics. So now let's take this formula and try to understand how does this formula looks like if you now go to different limit. So let's first take z fixed. So I look for the fixed angle and I send k to infinity. Then what you're expecting to find behavior which is 1, flat, no dependence on the angle. It's exactly what happened in this hadronization region, which was a region of extraordinary small values angle. But now what will happen, I fixed k and I send z to 0. Then this exponent in the denominator will dominate and you will have power-like behavior. So these two regimes, which you see in experimental data, naturally appear if you start from this very simple expression for this energetic relation in terms of this matrix element. So in this way, you went through this long procedure, we exploited different results coming from different fields, and finally we got something which conceptually looks similar to what you find in the experiment. Moreover, this formula also tells you that you're expecting to find the transition from one region to another for very special values for multiplicity, which scales with the angle like that. Basically, that's it. Let me conclude. So what I did, as I promised you, we started with some phenomenological observable energetic relations. So we started looking how we could compute it using different techniques. So we looked for simplified version of QCD n equal 4 theory. We found that using various kind of techniques, you could get this very interesting behavior at small angle, which seems to match what you observe in QCD, namely existence of these two different regimes for small angles and hadronization phenomenon, etc., etc. And last but not least, what this analysis shows you that if you're thinking about studying scattering amplitude, physical cross-section, etc., it seems like there is yet another parameter which appears on top of all others which we discussed so far. It seems like number of large particles, number of standing legs, could be used as yet another parameter, playing with which you could explore yet another properties of the observable. This is basically home-away message, which I believe is important in view of the potential application of this formula for another observable. Thank you very much.
Thank you very much for the, thank you for the very nice talk. Questions?
So, Grisha, did people try to get this energy-energy correlation in the simple phenomenological model where the jets are being formed by fragmentation of string splitting?
Yeah,
There's no relation to QCD at all.
I didn't say this, but if you look for this slide which I have shown you, this one. So what's shown here, these dots. So this lower panel, see the lower panel, it tells you difference between, let's say, theory and experiment. And you see there is different color. So different color corresponds because what people are doing, experimentalists, they simulate final states using different partonic branching. Another way, you start from the final state that have the quarks and gluons, and then there are different hybridization models which convert quarks and gluons to the hadron, and they just doing this kind of phenomenological calculation using different hybridization models. Hopefully that you're supposed to get, oh, excuse me, sorry. Hopefully that you should get the same result, and basically you see that all these curves, they more or less look the same. This more or less a posteriori proof the different partonic branching models that people used, different models. Lund hadronization, string hadronization, whatever. They give more or less comparable results in this case. But also notice that there is somehow, so this one is synonymous of saying C is equal to the experiment. Deviation from 1 means there is some non-P2P correction which you don't control. And you could see there is some contamination corrections around 1 and around 0. So I talk about this region. And you see that this picture already suggests you there is some non-P2P physics goes on in this region. This is basically what I was trying to explain. And there is yet another part, and this part also is worth exploring. And there are some interesting results coming from this region, which also could be interpreted in terms of some conformal data, etc., LOP, which I didn't have time to cover, but I could give you references if you're interested in it.
Thank you. More questions?
So everyone's favorite 4-point function has also been analyzed from the point of view of localization by these integrated correlator guys. So can you somehow reverse engineer that integration to sort of extract information?
As a matter of fact, good question. So this formula, this correlation function which I appeared here, sorry. Sorry. Yeah. So you see that here you have correlation function of HVPS operator with different weight. So the question is, what could you say about this correlation function? In principle, to compute energy correlation, you have to know this correlation function as a function of all coordinates. Recently, there was a lot of activity about computing so-called integrated correlators, which is another way of saying you start with this correlation function, which functions through cross ratios, and you integrate it over cross ratio with special measure. And this way, you're losing dependence of the coordinates. You're getting again something which functions of coupling constant only. And then you ask this question, could you do inverse engineering? Another way, using information about integrals to go back and reconstruct dependence on the coordinates. The answer was no, for arbitrary value of the coupling constant. But a strong coupling, it's possible. A strong coupling, you could use information about the correlators to reconstruct coordinate dependence of this correlation function. And actually, this formula which you see here, oops, excuse me. So this formula here, it was obtained using exactly this input. But in general, it's it's open question. Whether you could use information about integrated correlators, and there's many different, not only these integrated correlators, there are some other integrated correlators you could compute, whether you could use this information to reconstruct correlation function itself for arbitrary value of the coupling constants. I think these are very interesting questions, but as I told you, well, as far as I know, it has been answered only for this particular limit lambda to infinity, but in principle, these are very interesting questions to explore.
So on one of your slides, it was written that those energy correlators, they do not suffer from infrared divergences. Yes. Why is that?
Where do the infrared divergences come from? They come from the emission of particles with small energy. So imagine you're emitting particle with small soft energy, infinitely small energy, and you look for the contribution of this particle to your observable. So you have differential cross section, you have to integrate over variable phase space, and imagine if you have some soft particles in the final states, normally it's producing you logarithmic singularities. Another way, infrared divergence will appear like integral the epsilon over epsilon of the energy of soft particle. But once you go to energy-energy correlation, you will multiply this differential cross section by the weight factor corresponding to the detection of this soft particle. And the weight factor comes with the power of the energy. So therefore, you start from the integral, which was the epsilon of the epsilon, logarithmically divergent. You multiply by the epsilon, you get something which is infinitesimal, which is physically means that if you have particle with infinitesimal energy, they don't produce any contribution to something which are which sensitive to the energy of produced states. But this question is more deep than you might think, because what people experimentalists like, they like measuring various kinds of correlations. For example, not only energies, but for example, you have particles, hadrons, which are observed, they have various quantum numbers, including charges. And then you ask your question, could it be possible to measure not the energy correlation, but correlation of charges? Because these colorimeters, if you remember, at the beginning I've shown you a picture with, so there was different rectangles. So different rectangles on this plot, they correspond to computing different quantum numbers. One of them is energy, another is charge. And then we ask the question, is it possible, they measure correlation between charges, the experimental data. Then you ask the question, is it possible to compute those correlation between charges using perturbative Cousy framework? And you will find you're not, because these charge correlations, they're not infrared safe. They suffer from infrared divergences. And the reason for this is also quite obvious, because before I told you that energy correlation is special because they come with additional factor of the energy. But now imagine you have in the final state particle which has infinitesimal energy, but charge 1. You still have integral with respect to the epsilon of the epsilon, but doesn't matter how small the energy particle is, charge is 1. It doesn't depend on the energy. And that's the reason why this particle will produce infrared divergences. And infrared divergences in perturbative integrals is synonymous with this quantity actually is sensitive to physics at large distances. So it doesn't fall into the class of the observables which you defined previously, those when you're expecting the perturbative being suppressed. So therefore, message of this, that if you define different observables and you want to play this game, you have to be sure the observables called infrared safe. In other words, in perturbative expansion, you don't encounter any contribution coming from large distances. This is so for energy correlations, but I give example of quantity which is not. And in general, it's open question, which discussed by various people in different community. What will be the most general class of those infrared safe observables which could be measured and computed simultaneously?
Thank you.
Any more question? Well, if not, we can thank Gregory again.